Essay 65, Part 3. In the absence of a relatively simple and completely successful unified field theory, such as the 21st century Einstein Cartan Evans ECE unified field theory, the 20th century wandered mistily along on two different legs, one for electrodynamics, the other for gravitation, the former being special and the latter general relativity. So physics prior to ECE became incomprehensible and meaningless. It was two different philosophies riddled with errors. It is miraculous how expensive experiments were designed to test these errors and come up with triumphant precision. This failing of human nature existed in ancient and medieval times and has not changed one iota. It is a supplication to dense fog, one foot looking for the other. The idea of relativity emerged from the structure of the MH equations because Newtonian ideas do not apply in these equations. In Newtonian dynamics, a velocity is added to another to give the sum of velocities. Common sense in the 17th century. Common sense has a habit of becoming anthropomorphic. The sense is common because it is human, and by sense what is really meant is fogma. In Newton's time, adding one linear velocity to another could go on indefinitely, so that the result could ultimately reach infinity. Something could go infinitely fast. A signal from Earth could reach a distant star immediately, and in the terribly obscure 17th century language of physics, there could be action at a distance. Having based his work on this idea, Newton proceeded to reject it in that letter to Bentley. Pray do not ascribe, and so on. Newton could be as dogmatic as anyone and was not a particularly pleasant politician in his spare time from minting coins. In electrodynamics, however, it was realized by Maxwell that all that does not work. Light has a speed c which is thought still to be a constant in the vacuum to an excellent approximation. The latest claims made at incredible expense are that it may vary by a tiny amount from c in the vacuum. Maxwell realized that light is made up of electromagnetic waves which travel at c in a vacuum, but not in a material. That was Maxwell's greatest contribution to physics, in my own opinion. His equations are essentially unworkable, and it took a genius like Heaviside to unravel them at no expense at all. Maxwell realized that light does not travel faster than c. The first relativists, Heaviside, Fitzgerald and Lorentz, realized that it cannot travel faster than c and threw Newton away. The word relativity came into fashion because of the Lorentz transform, needed to explain the results of the Michelson-Morley experiment. Although challenged by a few contemporary thinkers, and they may be right, the Michelson-Morley experiment is to most physicists reproducible and repeatable. In the Michelson-Morley experiment, light is proven to be the same whether or not it travels with the Earth's rotation. The linear velocity v of the Earth's surface does not add to c. There is no v plus c. To the best of my knowledge, relativity as an idea started in correspondence between Fitzgerald and Heaviside, and after that with Lorentz. Neither Heaviside nor Fitzgerald had a clear way of putting their ideas into mathematics, but Fitzgerald wrote a half-page article introducing the idea that was used almost immediately by Lorentz in his mathematical work. Fitzgerald proposed it in words, Lorentz put it into mathematical format. The most famous part of that correspondence is the Lorentz transform. In my opinion, relativity began with the Lorentz transform, although Heaviside came very close to the right answer. Fitzgerald got the right answer in words. The Lorentz transform deals with the relative properties of two frames of reference, and hence the words relativity and relativistic. Considering two frames of reference can be terminally boring, but not to Lorentz. He must have played around a lot with different ideas before he hit on the right one. In real life, as opposed to the textbooks, this occurs very often, almost by accident. Foremost in his mind was the constancy of C. In any transformation from one frame to another, C must be constant because of the Michelson-Morley experiment. He was considering two frames of reference because Michelson and Morley had devised an experiment in which light was observed perpendicular and parallel to the Earth's direction of rotation. There could be a frame attached to the Earth, our own human vantage point, but there could also be a frame outside the Earth, a frame in which the Earth could move. For example, the Earth moves with respect to an observer at the center of the Sun, which itself moves with respect to a frame at the center of the Milky Way galaxy, and the Milky Way galaxy itself moves. Even so, it took a tremendous leap of imagination for Lorentz to go any further. He had to dispense with common sense. He had to change the meaning of a frame of reference, and he had to change the meaning of space itself. It could no longer be Newton's three-dimensional space, unchanged for 2,000 years from Euclid's time. The space of Newton and Euclid is independent of time. The idea that Lorentz hit upon is that time, as well as distance, can vary from frame to frame, but C cannot. I can imagine a hypothetical correspondence with Newton's wig falling off and "Pray do not ascribe any more" being hastily ascribed to Lorentz. In the comfortable 2,000-year-old dogma, received opinion, the square of a radius vector is constant if the vector is rotated about the origin of the frame. To make this idea clearer, consider the case of rotation in the plane labelled by axes x and y. Before the rotation, the vector is defined by components x and y, and basis or unit vectors, usually the familiar Cartesian unit vectors. After rotation, x and y change, but the square of x added to the square of y does not change, because the length of the vector is not changed by a rotation. This familiar idea is the point from which Lorentz took off. He added the third dimension z and denoted the sum of x squared plus y squared plus z squared by r squared. Where does a constant c come into the theory? The Lorentz transformation postulates that c squared t squared minus r squared is constant in any transformation from one frame to another. This difference in terms, c squared t squared minus r squared, is denoted c squared tau squared, and tau is named the proper time in the admittedly terrible jargon. Therefore, time multiplied by c becomes a fourth coordinate, and space is transformed into spacetime. The position vector becomes four-dimensional and has four components. It is denoted by ct xyz instead of xyz. This is known as a contravariant position vector. Minkowski later realized that an elegant formulation of special relativity can be achieved with the use of the covariant position vector ct minus x minus y minus z. The key idea of special relativity is that time in one frame of reference is different from time in another. Special relativity reduces to one idea that time can change from one frame to another, but C cannot. So there must be experiments that can be devised to test this idea. The proper time tau is the square root of 1 minus v squared over c squared multiplied by t. If a particle is observed to be moving at a velocity v with respect to an observer, the latter measures a time interval delta t in the observer or laboratory frame k. The proper time interval measures the time in the frame in which the particle is at rest. It is the particle's own frame. For example, the proper time interval is the time for a passenger on board a plane. The passenger and his watch is at rest with respect to the plane. The proper time interval is smaller than the observer time interval. So a watch on board a plane may record that 1 hour has passed, but for a watch on the ground, 2 hours have passed. Time on board the plane is slower than time on the ground. In other words, the watch on board the plane runs slow. This phenomenon has been verified experimentally to astonishingly high precision, and this is meaningful relativity, worked out not by Einstein but by Lorentz and others such as Voigt, long before Einstein's work of 1905. The jargon is horrendous, and the phenomenon is known as time dilatation. All that it means is that the watch runs slow on board a plane. This type of relativity was developed elegantly by Lorentz and Poincaré in the context of electrodynamics, using the then new tensor methods of Levi-Civita, Ricci, Bianchi and others around 1900. A tensor is a kind of matrix. It can exist in one dimension as a row or column matrix, and then becomes a vector. A matrix can exist in any number of dimensions. One of the most elegant parts of the least phlegmatic type of physics is the expression of the MH equations in tensor format. There is one homogeneous tensor equation and one inhomogeneous tensor equation. The electromagnetic field is expressed as a 4x4 antisymmetric matrix and is known as the electromagnetic field tensor. The elegance is revealed most clearly when one realizes that the Lorentz transform is worked into the field tensor, which transforms into another frame using the transform twice, i.e. the transform applied to a tensor, and gives the Lorentz force equation. This formulation is therefore covariant and a valid theory of special relativity. The field tensor is expressed in terms of the derivatives of the four potential, which combines the ideas of scalar and vector potential used by Heaviside. In this early theory, the Poincaré lemma can be used to show that there cannot be a magnetic monopole. Many scientists argue that a magnetic monopole can exist, but the experimental evidence is still debated. In ECE theory, the existence of a magnetic monopole is left as an open question. All these great achievements were made when Einstein was still a student, a very bright one, confident with a clear grasp of concept, but prone to mathematical errors and impatience. End of part 3.